find the two tangent lines to the parabola y equals x squared, which will perpendicularly intersect somewhere along the line x equals 3/8. So to help understand what we're looking for, here's a parabola, not just any parabola, the parabola y equals x squared. And we've also marked this dotted line. Here's this line. This is the line x equals 3/8. Now what will happen is for any point you pick, there's going to be a tangent line, and any tangent line you pick, it's going to pass through x equals 3/8 at some point. So there's infinitely many tangent lines passing through x equals 3/8, all over the place. And they're really sort of coming from two different sides. So the question becomes, all right, let's find some which intersect. Well, that's not so hard. Usually you'll have something that goes up towards the right and something that heads off to the left. But now it says, look, it's not just enough that they intersect. They have to intersect and be perpendicular. All right. So that's our goal. That's our goal. Now to help us get to that goal, we should remind ourselves a couple of things. So first off, we're after a tangent line. And we said, well, last time we want a tangent line. They have the following form. Y equals the function at a plus the derivative at a times x minus a. And that's just a generic expression for tangent lines. Now, in our case, our function, we're dealing with f of x equals x squared. So we should probably sit down and quickly compute what f prime of a is, because f of a, that's pretty easy. That's going to be a squared. So f prime of a, from last time, that's the limit. H goes to 0. F of a plus h minus f of a all over h. Limit h goes to 0. Quantity a plus h squared minus quantity a squared all over h. So limit h goes to 0. A squared plus 2a times h plus h squared minus a squared all over h. And at this stage in the computation, you should say, look, I'm a good person. I've done good things in my life. I should get cancellation. And it does. It should always cancel at this stage if you're working with polynomials. If you're working with something more complicated, you may have to do a little bit more to get to that point, but you should get cancellation. So in particular, that everything left has an h in it. So dividing through by h, we get a limit as h goes to 0 of 2a plus h, so we get 2a. So that goes into our f prime of a. So at this point, we can say, aha, our generic tangent line looks like the following. A squared plus 2a times x minus a. Or if you rearrange that, that says y is 2a times x. Then you have an a squared and a minus 2a squared. So that becomes minus a squared. So this right now, that's our generic tangent line. Now the reason why I want to get to the stage where there's the generic tangent line is we're looking for some tangent lines. So oftentimes if a problem says, well, find the tangent line which has this property, what we do is we say, all right, I'll just find all the tangent lines. And then I'm going to sort through the tangent lines and pick out the one, or in this case, the two, that give me what I need. Now, what do? Well, we know a couple of things. We know that, say, this is our first tangent line. So this is tangent line at A. We'll also look at the tangent line at B. So I'll say that's 2bx minus b squared. There's a couple things that have to be true. First off, they have to intersect at this x equals 3/8, which means that if I put 3/8 into both sides, I should get the same value. So if we look at 2a times 3/8, subtract a squared, that should be equal to 2b times 3/8, subtract b squared. Now, this perhaps does not seem the most informative, but let's see if we can't extract a little bit of information. Now 2 times 3/8 is 3/4, so I can write this as 3/4, and notice there's an a here. But there's also a 3/4 b. I'm going to bring that over. So I'm going to write that as 3/4 times a minus b. Then I'm going to have what? Well, a squared, but then I'm going to bring the b squared over. So I can subtract a squared minus b squared. Set that equal to 0. So I'm just moving everything over. Now at this point, we should say, something very familiar. A squared minus b squared. What can be done with that? A minus b, a plus b. And so I say, well, both terms have a minus b. So I could pull it out. So I get a minus b times 3/4 minus a plus b. That's got to equal 0. Now there's two possibilities. Now one possibility is that a equals b. Are we interested in that scenario? No, we're not interested in that case. Why aren't we interested in the case when a equals b? Because they're not different lines. It's the same line. See, we want to find two different lines. So here we can say, look, it's not the case that a equals b. And therefore, we can conclude that a plus b, whatever they turn out to be, they better add up to 3/4. We haven't found them yet, but we know that if we add the two values together, whether we take the tangent lines, it better add to 3/4. So that comes from the requirement that they both intersect at the line x equals 3/8. So we haven't used everything yet. What haven't we used? Or what fact haven't we said, okay, we also must do perpendicular. We haven't said anything about perpendicular. All right, so when are two lines perpendicular? Slopes are negative reciprocals. What's the slope of the line y equals 2ax minus a squared? 2a. What's the slope of the line y equals 2bx minus b squared? 2b. So we also need that 2a is the negative reciprocal of 2b. In other words, 2a is negative 1 over 2b. Now we can rewrite this. That says 4 times a times b had better be equal to negative 1. And now we're in pretty good shape because we have two equations and two unknowns. So how can we go about solving? Well, this is a good time to substitute. So, for instance, the first equation, we could say that b is 3/4 subtract a. Now we can take this information and plug it in for b in the other equation. So 4 times a times 3/4 minus a better be equal to negative 1. If we multiply the 4a through, that tells us that 3a minus 4a squared should be equal to negative 1. And then we can move everything to the other side. So we get that 0 should be equal to 4a squared minus 3a minus 1. Now, if we're lucky, it factors. If we're not lucky, all right, we throw it into the quadratic formula. Are we lucky today? Yes, we are. The math gods have smiled on us. What does it factor as? 4a, you said 4a plus 1, a minus 1. Well, let's check. 4a squared, that's good. Minus 4a plus a, minus 3a, right? And then minus 1. So, what do we get for a? Well, we get a equals 1 or negative 1/4. Now the question is, what's the right answer? The answer is they're both right. Because see what happens. Suppose for a second you said a equal 1. What's 3/4 minus 1? Negative 1/4. Suppose a is negative 1/4. 3/4 minus negative 1/4? 1. So it's really just a matter of saying, okay, which one do you call A and which one do you call B? There's nothing that said that A had to be below B when we chose it. So the moral is the tangent lines are coming from 1 and minus a fourth. Now, are we done? You should be suspicious because I just drew a box as if to indicate we're not done. So, are we done? What? Well, what we found was we found A and B. What are A and B? A and B are where the tangent lines occur at. What were we asked to find? The tangent lines themselves. See, these are not lines. What these are locations that we should take the tangent lines of. So what we need to do is make sure we end up with a line. Well, how do we do it? We plug these back in. So for example, I take A equal 1, I can plug it into my generic tangent line. I'll get y equals 2 times 1 times x, known as 2x, and then minus 1. Or if I plug in negative 1/4, 2 times negative 1/4, well, that would be minus a half x, and then I'm going to have minus negative 1/4 squared. That's minus 1/16. And that's the answer. So those are the two lines. They're both tangent to the curve y equals x squared, and if you draw them, they are perpendicular to each other and they intersect on this line at x equals 3/8. And there you go. Now you might say, I probably could have guessed those answers. Just tried around and maybe fudged and found them. And that's true because we chose the answer to be nice. But here's the great thing. Even if the answer hadn't been nice, we still would have found it. It just wouldn't have been as pleasant looking. See, the important thing is we have a method. And the method is the important thing. All right. So last time we talked about derivatives. Today, we're also going to talk about derivatives because it turns out derivatives are really important in calculus. So we're going to talk about, first off, a little bit about functions. Now, the way I like to think about functions is it's a rule which takes some input, does something to it, and then you produce an output. Now, oftentimes we think about a function of the formula y equals f of x. So that the input is x, you run it through your rule, and the output is f of x. An example of what I mean by the rule is we can talk about a function we just did, where f of x equals x squared. Here, the inside part, this machine says, whatever you put into it, just square it. And that's what the rule says. Now, one thing to keep in mind is that once you understand that a function just says, you take an input, you do something to it, you produce an output, you see that functions are actually really general. And you can do all sorts of fun things with functions. Now, a function that students really care about at the end of the semester is where you put in a student, put in their grades on the exams, put in their scores on the quizzes, and out comes a letter. A to F. Students really care about that function. They've even given it a name. They call it the curve. And this is probably the most studied function of any function in calculus is the curve. But, well, we'll find out about that later on in the semester. But, all right, so one of the things we can do, and maybe it's not the most obvious thing, is to say, wait a second, if I can put anything in, how about I put in just a function? Is that allowed? And the answer is yes, you can actually do that. So there's something called an operator. So from time to time you'll hear something about the derivative operator or the integral operator. So what that is essentially it's a function on functions, where what you do is you throw a function into this machine, out comes a new function. So as an example for us, the one we care about is we have this thing called the derivative. We put in a function, it does something, and out comes this thing, f prime of x, which has a nice important meaning for us. So last time, we did talk about the derivative, but when we talked about the derivative, we really said, okay, let's talk about the derivative at a single point. So in other words, what's the derivative at 1, which is the same as saying what's the slope of the tangent line at 1? What's the derivative at 5? What's that slope of the tangent line at 5? But we can say, all right, look, let's not just worry about one particular point. Let's just do all the points. So I can create a function here. So now it's really, I'm thinking of it as a function with an arbitrary input. So f prime of x. And so the big new idea is we came in, last time we had like a's, today we have x's. Wow, what a difference. Okay, well, it's more or less the same. Now, keep in mind, there are some things here. If you ever hear the word differentiable, it's just another way of saying it has a derivative. A nice way to think about differentiable is to say, all right, a function is differentiable if I can find a derivative, which means that locally I look flat. And this is going to be an important idea when you take multivariable calculus later on. So differentiable functions are nice functions. They're functions which locally they look flat. So here's a claim, or rather here's an example. Show that the function f of x equals x squared is a differentiable function. We kind of did that already. Let's kick it up a notch. Let's go 3. X cubed. All right, let's do that one. So what do we want to show? Well, what we want to show is that when we apply the rule, in other words, compute this derivative, we always get something out. So if we get something out, it's differentiable. So we say, okay, f prime of x, that's the limit as h goes to 0, f of x plus h minus f of x all over h. Well, that's the limit as h goes to 0. And now I'm plugging in x plus h. So x plus h cubed minus x cubed all over h. Well, now we cube it. Now it would be really nice if it was simple to take the cube. It's not too bad. Now there's a very big temptation, which is to say x plus h cubed is x cubed plus h cubed, because that would be easy. Now there's this one small problem with that. It wouldn't be right. And remember, our goal is to get all the points. So if you were to do x plus h cubed, you can either work it out, or you could say, I paid attention in algebra. That's 3x squared h plus 3x h squared plus h cubed. That's what it turns out to be. So you may have heard something called binomial expansion, binomial theorem, and that's how you get these things. Well, we're good people. We've taken care of ourselves, so what should be true? You get cancellation. The x cubes cancel. Essentially, that original function knocks itself out, and then everything else has an h in it. So that's the limit as h goes to 0. You can divide h into each term. 3x squared plus 3xh plus h squared. As h goes to 0, what do you end up with? 3x squared. All right, so the question is, was this differentiable? And the answer is yes, it's differentiable because the derivative exists. We actually get an answer out. If the limit did not exist, the function would be not differentiable. Now, oftentimes we talk about being differentiable at a point, but we can talk about being differentiable everywhere. And some functions have like a single problem. As an example, we already saw this. Absolute value of x is not differentiable at 0 because the derivative didn't exist. It had that V shape, and no matter how far you zoomed in, you wouldn't be able to make it look flat. All right. Well, one of our favorite things to talk about now, notation. So when we're talking about derivatives, there's a lot of different notations out there. The main one we've already been using is the prime. And that's just a convenience, so to speak. There are people in the math department who are not big fans of the prime notation because it's not really telling you what's happening. stumble across it in the dark and be able to say, oh, it's obvious what's going on with this derivative. So there's another type of notation which uses a dx notation. So if you ever see d dx, that's a shorthand for saying I'm trying to take the derivative with respect to x. Essentially what you should see if you ever see a d something, is you should say, oh, I'm trying to look at what happens when I have a small change in. So the d can stand for a small change in. So I'm trying to say, what's the small change of whatever I'm looking at when I look at a small change in x? That's what the d dx notation becomes. So we can write f prime of x, or we can say, well, what's changing, what's the result of our f of x when we look at a small change in x? So that's what this notation means, d dx. It can also be written as df dx. We usually, instead of df dx, we write dy dx for what's a change in y over a change in x. Now, if you think about it that way, you're like, okay, so that's how it connects in. Because we talked about this tangent line, and the slope of a tangent line, that's a rise over a run. So a change in y, that's our rise, and a change in x, that's our run. So dy dx, okay, that's like a slope. Another common notation is y prime. These are the ones you should be comfortable with. Now, these are not the only notations that exist for derivatives. So some other ones that you might see later on, some people use a capital D because derivative starts with the D. So, all right. You might also see a capital D sub x. And that's going to be more common when you get into multivariable calculus, when you have many things which could be varying, and hence the name multivariable. And if you go old school, dig back and say, I'd really like to read what Newton wrote on the subject of calculus. I'm going to go learn Latin so I can read what Newton said. You'll see that he had a different notation. He put it with a dot on top. So f with a little dot. Now, that still exists in some disciplines. So depending upon what you end up studying later on in life, you might come across that. But it is somewhat rarer these days. There is a bias, I will say, because Newton was from England, and the other person who is often discussed is Leibniz, who was from Germany. Leibniz preferred the d dx notation, whereas Newton did the dot notation. So there's a tendency for mathematicians in England to sometimes lean towards the dot. National pride. Well, all right, whatever. As long as we get the math right, I guess it works out. So don't interpret that to mean you can start using dots. Use the notation that is the common notation. You might also need to say, I need to take the derivative at a certain point. Because remember what a derivative represents. We've talked about the derivative as being a slope of a tangent line. But that's when we talked about derivative at a point. So when I have a derivative as a function, like that f of x was x cubed, that f prime of x was 3x squared. 3x squared is not a slope of a tangent line, it's a function. So how do you get to that slope? The answer is you evaluate. So if you want to evaluate, you simply plug in the right value into the derivative function. Now there's other ways to denote that. You could say dy dx with this vertical bar at x equals a. So when you see a vertical bar, think of that as saying, oh, I need to do an evaluation. I need to evaluate at a certain point. Sometimes you'll see the derivative at f of x evaluated at x equals a. So suppose I want to find the derivative of the square root of x at x equals 25. Now there's a couple ways to do this problem. One way is you can say, oh, I just need to do the derivative at a point, and my point happens to be 25. And so work through the definition from last time. Another way to do this, which is probably the way we'll do it now just because practice is good, is we'll say, well, let's just find the general formula for the derivative of square root of x, and then once we have that, we'll plug 25 in. So here we go. The derivative of square root of x. Well, that's the limit. H goes to 0 of, now what's our function? Our function is what we're taking the derivative of. So if we go back to our terminology of operators, we're taking the derivative operator of square root of x. So here, our function is square root of x. So square root of x plus h minus square root of x all over h. This time, it's not just a matter of simple, oh, it cancels out. We've got to work a little bit. So what can we do to help us make progress? Conjugate. Yeah. Isn't it cool that we learned all these useful things like algebra, so that when we came up to these problems, we I know what to do. I've got the tools. Multiply top and bottom by the conjugate. If we do that, what will the top become? X plus h minus x. Downstairs, don't multiply it out. Leave it alone. All right. Now, because we're good people, what should happen? Get some cancellation going. The x's cancel. What's left now on top? H. Well, there's an h on the bottom, so I can cancel off the h on the bottom. And therefore, this becomes the limit as h goes to 0 of upstairs is 1, downstairs square root of x plus h plus square root of x. So we plug in h equals 0, because that's usually the rule of thumb is, okay, we've canceled, let's see if we can now plug it in and get something nice coming out. We'll get 1 over square root of x plus square root of x, which is 1 over 2 square root of x. So now we know that if I want to take the derivative of square root of x, the answer is 1 over 2 square root of x. But remember, I didn't want to just take the derivative, I wanted to evaluate it. And therefore, I could say, look, the derivative of square root of x, evaluated at x equals 25, is the same as 1 over 2 square root of x, evaluated at x equals 25. So that would be 1 over 2 times the square root of 25, and square root of 25 is 5, so that leaves us with 1/10. And that's the answer. All right, well, let's try another one. I think we have enough time left in class that we could probably finish this one. How bad could it be? No, come on, it's not going to take that long. It's not going to take that long. Of course, there are people who've taken calculus before yeah, it's going to take a while. Strap yourself in, my friend. It's going to be here for a while. All right, so suppose you want to take the derivative of x plus 1 over x squared plus 2. At first glance, this does not look like the most pleasant thing to take a derivative of. This is one of those cases when you can judge a book by its cover. So here we go. Practice. I think the one thing we're going to get from this example is appreciation of how much we don't want to work with limits. So if you get nothing else from this example, just I'm looking forward to when we can get rid of limits completely. All right, so what do we get? This is the limit as h goes to 0 of, good news, downstairs is easy, h. Upstairs, it's x plus h plus 1 over x plus h squared plus 2, sorry, bad handwriting there, minus x plus 1 over x squared plus 2. All right. So I took in, and I said, look, everywhere there's an x, I put in an x plus h. Subtract, just put in x. In other words, f of x plus h minus f of x. Now what comes next? You want a common denominator. All right. So this would be the limit as h goes to 0. So common denominator, I would do the following. On the first number, the first fraction, that's x plus h plus 1. I'd multiply that by x squared plus 2 over x squared plus 2. On the second one, which is x plus 1, I'd multiply that by x plus h squared plus 2. Well, if you square that out, that's x squared plus 2xh plus h squared plus 2. All over x squared plus 2, there, and x plus h squared plus 2, all of that, all over h. Okay, well, what comes next? We can move the h up, has been suggested. In fact, we can. If you think of it as like h over 1, think about multiplying the top and bottom by 1 over h. Then downstairs you get 1, so that knocks it out, and you get a 1 over h. So the good news is we got rid of our fractions within fractions. What's the next thing to do? Well, next thing is work on that numerator. Okay, so we're going to foil. But not just any foiling. This is some hardcore foiling. Because this isn't just a two terms type, two terms. You know, you'll notice, for example, here I have 2 terms, here I have 4 terms. And this is the kind of foiling where you're going to run out of space. But all right, we start working. The rule of thumb is every possible thing from the first times every possible thing from the second. So x times x squared, that's x cubed. X times 2, that's 2x. H times x squared, that's h times x squared. H times 2, that's 2h. Then 1 times x squared, that's x squared. And then 1 times 2 is 2. Okay, that's if you expand the first term. That's the easier one. Subtract. So this is all the numerator here still. And downstairs will be the same. You can see I'm delaying the part I don't want to do. Okay, here we go. X times all of that. Well, so x times x squared, that's x cubed. 2x times x is 2x. Oh, sorry, 2x times 2xh. Sorry, x times 2xh. I'll say the right word eventually. That's 2x squared h. X times h squared, that's x times h squared. X times 2, that's 2x. Then plus 1 times everything, so plus x squared plus 2x h plus h squared and plus 2. Okay, now, assuming we've led a good life and done our algebra correctly, what should happen? A lot should cancel. Let's see if a lot cancels. In particular, I'm looking at things which don't have h in it, and they should cancel out. This is an x cubed. It doesn't have h in it. There's a minus x cubed. Those cancel. Here's a plus 2x. There's not an h there. And there's a minus 2x. So those cancel. Let's see. What else? There's an x squared. And, oh, there's an x squared. Those will cancel. Plus 2. We'll cancel with that 2. Now, those things should absolutely cancel. If we're lucky, we might get some more cancellation and more simplification. Let's see what's left. So, we now have a limit as h goes to 0. Looking at all the terms that remain, everything that's left does have an h in it. So I'm going to go ahead and factor an h out. So we have h times x squared plus 2. Then we have minus 2x squared, so we'll clean that up in a second. Minus x times h. Then minus 2x, because remember we pulled that h out. Then minus h. And downstairs, oh, whoops, I forgot the 1 over h. There's a 1 over h there. Downstairs we have that h still, x squared plus 2, and x plus h squared plus 2. Now, here's the great part. What cancels? The h's cancel. So, we're right there, ready to wrap it up. What's our last thing to do? We can plug in 0 and see what happens. Now, when we plug in 0, that's going to go to 0. And everything on top that had an h in it will also go to 0. So, we can conclude, well, downstairs, it's x squared plus 2 times x squared plus 2. So that's x squared plus 2 squared. Upstairs, we have x squared minus 2x squared. That's minus x squared. There's a minus 2x, and then there's a plus 2. And there you go. Nice. Well, maybe that wasn't so bad. Maybe we can keep limits. Oh, all right. Let's try something a little different. Let's find dx dy given that x equals y cubed plus y. So we're not going to work very hard on this one, but because we've already done things like taking the derivative of a cube. But let me ask the question, can we ask, like, what is dx dy? Does that even make sense to ask? The answer is yes, it makes perfect sense. See, there's nothing sacred about names. X and Y's are just simply convenient names. And we can change names and we can have them swap out. So what are we really asking here? So when it's saying find dx dy, given that x equals y cubed plus y, it's really saying take the derivative with respect to y of y cubed plus y. That's what it's saying. And that's a perfectly valid question to ask. How is this thing y cubed plus y changing as I'm changing y? That's what the question being asked is. Now, given that we've already taken the derivative of the cube function, what should be the derivative of y cubed when we take the derivative with respect to y? Yeah, it's 3y squared. And derivative of y, how is y changing as we're changing y? Well, the answer is they're changing at the exact same amount, so it's plus 1. All right. Here's another problem. This one we're going to do out properly. We're going to do it all the way. So, let f of t be equal to t squared minus 4 divided by t squared plus 2 quantity squared plus 4 over t squared plus 2. Now, your first reaction is maybe I'd rather just not get the points for this one. You know, I get to drop a problem. This will be the one. But that should not be your reaction. What you should always look at when you say a problem, you should always think of, is this really the problem that I've been asked? Or are they obfuscating something? By that we mean, maybe they haven't written the function in a very convenient way. Before I jump and try to do a lot of hard work, let me see if there's a better way to think of this function. So let's think about it. How can we rewrite this function to maybe make it more clear what's going on? Well, we can get a common denominator, right? They both have t squared plus 2, but this one's squared and this one's not. So let's make them so they're both squared. So that's t to the 4th minus 4 over t squared plus 2 squared. And here you'd multiply by t squared plus 2 over t squared plus 2. So you get 4 times t squared plus 2 over t squared plus 2 squared. So now we've got a common denominator. T squared plus 2 squared. Upstairs we'd have t to the 4th. Then here we'd have 4t squared. Then we have a minus 4, and plus 4 times 2 is 8. So plus 8. Well, maybe that looks a little bit better. Can we go further? Sorry, minus 4 plus 8 is plus 4. I can do math. Can we go further now that we have the right thing? Yeah, what can we do? Foil the bottom. Oh, that's a bold move. All right. I would have gone with factor the top, but okay. Foil the bottom. We'll go ahead and foil it out. What do you notice? They're the same. So our function that we're asked to take the derivative of is the function 1. So the moral here is I can take this derivative and do something like that, and, you know, I might be crying a little bit. Or I can say, wait a second, let me take that derivative, in which case I'd be happy. Okay, so the moral is, what's the derivative? Well, if our function is 1, the derivative of a constant is 0. because derivatives are talking about change. If your function is constant, there's no change, and therefore the derivative is 0. Okay. Now, from time to time, we will consider what are called one-sided derivatives. And essentially, if you think about limits, we talked about, well, if you have a complicated limit or a limit of a piecewise function, what you can do is you can say, well, what happens as you come in, say, from the left, and what happens as you come in from the right? And by considering these two different things, we can understand the behavior by putting them together. So in terms of one-sided derivatives, and we're not going to dwell on this much, I just want to say that this exists. The moral is, well, derivatives have this limiting idea underneath them. And so a one-sided derivative is when you have a one-sided limit. So from the right-hand derivative, take the limit from the right. Left-hand derivative, limit from the left. So if I have the derivative of y equals square root of x, I can take a right derivative because I can actually talk about what happens to the function to the right of 0 at square root of x. I can't talk about what happens to the left of 0 because the function would be undefined. So what's the answer? Well, it's the limit as we come in from the right-hand side, or if you like from above, of our function. So this is our f of x here. So it'd be f of 0 plus h, because we're at a particular point, minus f of 0 all over h. So that's the limit as h goes to 0 from above, square root of h minus square root of 0, which is 0, over h, which is the limit as h goes to 0 from above. If you simplify, you get 1 over square root of h. And what happens to that as we let h go to 0? Well, you get like 1 over 0, and 1 over 0 means, well, something's blowing up. You have a number divided by a very small number. And we can even go a little bit further. We can say that very small number is a positive small number. So this is going to infinity. Now the way you can interpret that is to say, if you look at the square root of x line, and you say, well, what's happening at 0? Well, what's happening at 0 is it's essentially going straight up and down. So it has a vertical tangent line. So you might see behavior like this happening when you have vertical tangent lines. So there are other functions that have this behavior as well. So let's suppose we have the following. Find the left and right-hand derivatives at 1 for f of x, where our function is x a fourth if we're below 0, 2x squared minus x if we're between 0 and 1, or x cubed if we're above 1. And then the question is the function differentiable at 1? Well, we will tackle that question later on. So we're going to take a look at the limits really quickly. So as we come in from above, so we look at f of 1 plus h minus f of 1 all over h. So let's see if we can figure this out. What is f of 1? Well, plug in 1. This would be the rule, because there's this equals 1. 1 cubed, that's 1. So h goes to 0 from above, something minus 1. Because we're above 1, see 1 plus h would be above 1, we're going to be in the rule of 1 plus h. So 1 plus h cubed minus 1 all over h. And we've done this before. In fact, we talked about the derivative of x cubed already today. So we know that this is going to simplify. And so in the interest of time, this becomes 3. It's the same thing we did before. You have 1 plus h cubed. You can expand that as 1 plus 3h squared plus h cubed, and simplify. So that says, if I were to look here, I think the derivative should be 3 if I look from above. If I look from below, limit as h goes to 0 from below, f of 1 plus h minus f of 1 all over h. Well, that's the limit as h goes to 0 from below. Now, I'm below 1, so I use a different rule. So 2 times 1 plus h squared minus 1 plus h. Then I subtract 1 all over h. So if you clean this up, that's the limit as h goes to 0. You get 2 minus 1, which is 0. Then you're going to get, in the cross terms, you're going to get 2h times 2 minus h, so that's 3h, plus 2h squared over h. There's algebra here, but we like algebra. We're almost on a first-name basis with algebra now. We just call it al. All right, cancel out the h's, 3 plus 2h, and lo and behold, you get 3. So, as we come in from the right-hand side, we think that the slope should be 3. As we come in from the left-hand side, we think the slope should be 3. So the question is it differentiable? Well, to be differentiable, I need to have a slope. And so, do these match? Yeah, they do. So, we can say, yes, differentiable. And what's the tangent line? Well, the tangent line, these 3 tell us that our slope is 3. So we get that y would be equal to the function at 1, which is 1, plus 3 times x minus 1. So f of 1, this is f prime of 1, and then x minus 1. Now this is not quite so trivial as you might think, because I asked the question at 1. Now we could have talked about 0. Now if we were to sketch this curve, and I'll try to sketch a little bit of it here, what you would see is the following, is that you have x to the 4th, which comes down, and it comes down nice and flat at 0. All right. Now you get 2x squared minus x. And 2x squared minus x, that's a parabola. That probably doesn't surprise you too much. And what it does is it looks something like this. So that we come up here, and here's 1. And then x cubed keeps going. So the part here where we looked at, they actually come together fairly smoothly. So even though beneath it, it's a parabola, and above it, it's a cubic, at the point where we glue them together, they lined up in not just that the functions lined up, but if we zoomed in, the slopes lined up. But wait a second, what's happening at the origin? What do you see there? Well, if you zoom in, what you'll see is it's flat from one, but then going down from the other. The slopes don't line up. Is the function differentiable at 0? No. So it's not enough to be continuous. Now there is something which is nice to say, and it's the following. If our function is differentiable, it has to be continuous. But remember, it's not the other way around. Continuous functions don't have to be differentiable. But if you're differentiable, you have to be continuous. So the intuition is just to say, hey, if I'm differentiable, that says locally I look flat. And it means I look like a line, and lines are continuous. So I'm going to be a continuous thing. Now, a mathematician wants to make this sound more complicated. So what they do is they say, hey, here's the way to justify it. I just have to check, do what I expect to happen, is that the same as what does happen? And the answer is I say, oh, I can multiply and divide by an x minus a, I mean, adding f of a. And if you look, this is just a really complicated way to write f of x. But the pieces are nice to work with. The first part goes to 0. Sorry, the x minus a goes to 0. This part goes to something because it's differentiable. So you end up with the f of a. What you want to happen is what does happen. And so you can ask the following question. Really quickly, we can answer this one. Is the following function differentiable? I'm going to sketch it for you. Sine of 3x does this. E to the 4x does that. Is it differentiable at 0? No, because it's not continuous. If you're not continuous, automatically not differentiable. All right, that's it for today.